Welcome back to The Deep Dive, the show where we take a complicated stack of research and turn it into the essential knowledge you need without the headache.
Mm.
Today, we're digging into the engine room of modern software, a piece of technology that quietly powers most of the integrated web, from payment processing and deployment pipelines to instantaneous logging and notifications. We are talking about webhooks.
Yes, we are.
And our mission today is to move far beyond, the Wikipedia definition. We're going to conduct a true deep dive into the architecture, the non-negotiable security layer built around HMAC, and most importantly, the hard-won trade-offs you have to understand when adopting this crucial paradigm for service-to-service communication.
Mm-hmm.
You'll walk away not just knowing what a webhook is, but really understanding the engineering complexity required to build, secure, and scale one effectively.
That's a perfect framing because webhooks are, frankly, the essential glue holding the distributed web together. But they're often the source of some really unexpected complexity. They operate under a few different aliases in the industry. You might hear them called HTTP push APIs, maybe HTTP callbacks, or sometimes even reversed APIs.
Reversed APIs, I like that one.
Yeah, but the function remains immutable. They fundamentally enable one service, which we'll call the source, to send a message to a separate service, the destination.
Okay.
The very moment an event occurs, without that destination service ever having to explicitly ask for the data, it flips the standard API relationship on its head.
Okay, let's unpack this. Because the entire architecture hinges on a foundational concept we need to fully appreciate: the callback.
Absolutely.
We can start with a simple, kind of familiar analogy.
Right.
Imagine you call a key business contact, but they're stuck in a meeting.
Right.
They don't want you to keep calling back every 5 minutes to check if they're free. Instead, they give you a promise. Give me the specific line to reach you on, and the moment my meeting ends, I will call you back.
Mm-hmm.
That promise to initiate contact later is the callback.
It is. It's that simple.
In the world of APIs, then, a callback is just an application interface, almost universally an HTTP endpoint, that is designed, implemented, and exposed by the destination service, specifically to receive and process those incoming unsolicited messages.
Yeah.
It's the open line, just waiting for the event-driven notification.
And that analogy helps us perfectly visualize the formal communication flow. The source material outlines this flow in 3 distinct phases, they're really critical because they define the separation of duties.
Okay, what are they?
Phase 1 is registration. The destination service, the one that wants to be notified of, say, a payment success or a configuration change,
Right.
it actively registers its callback, that specific URL within the source service. This is the give me your number step.
Okay.
Phase 2 is execution. The source service is constantly listening for the specific events it's configured to track. The instant that event occurs, an order is created, a file upload completes, a repository receives a commit, the source service sends a message instantly. That message is an immediate HTTP request, almost always a POSOF, directed to the destination's registered callback URL.
In phase 3.
And phase 3 is acknowledgement. The destination service, having received and processed the message, must immediately send an acknowledgement back to the source service.
Usually what, like an HTTP 200 response?
Typically an HTTP 200, yeah. And this response is critical. It confirms the message was delivered and accepted for processing, and as we'll definitely discuss later, it forms the whole basis of reliability.
That distinction between the registration and the execution is key. So the defining feature of webhooks is this fundamental push model, right? They are an HTTP request that is triggered solely by a state change or an event in the source system.
Exactly.
This request is sent instantly, carrying a specific structured payload, often JSON detailing exactly what happened, and delivered to a callback URL that the destination predefined.
Right. And we should probably pause here for a moment on terminology because confusion often arises. We commonly describe webhooks as server-to-server communication, and while that's technically true, it kind of muddles the formal client-server relationship.
How so?
Well, in the strict definition, the server is the one awaiting the connection. When service A, the source, sends a webhook to service B, the destination, service A is initiating the connection. It's acting as the client. Even though A is generally a back-end system, service B is passively waiting to receive, so it's acting as the server.
Ah, I see. That could be confusing.
It can be. To avoid that cognitive dissonance, it's always cleaner and more universally accurate to just stick to the terms source service and destination service.
You're right.
The source produces the event and pushes the data. The destination consumes the event and defines the receiving endpoint. Simple as that.
It's about the direction of the data flow, not the permanent role of the machine. Understood. But this leads us naturally to the history. This push model, I mean, it isn't just a new feature. It's a philosophical rejection of the old web model.
It really is.
How did this pattern emerge, and what fundamental problem did it solve?
Well, the term webhook, originally 2 words with a space, is famously attributed to Jeff Lindsay, who laid out the concept in a blog post way back in 2007. This was a direct response to the limitations of the existing request-response paradigm.
Okay.
And Lindsay's core inspiration came from thinking about how simple, reusable programs are chained together in Unix environments using pipes. This analogy is it's incredibly powerful for understanding webhook architecture.
Ah, the Unix pipe. It's the original standard for data flow automation. For those who might not have spent time at a command line, a pipe lets you string together separate programs. The standard output, or stout, of program A is automatically connected to become the standard input, or skidin, of program B. The programs don't need to know anything about each other's internal logic. They just know they're exchanging a data stream.
Exactly. Lindsay imagined the web operating under this same principle. Why should one web service, having completed a task, only communicate the result when explicitly asked?
Right, why wait?
He envisioned using an HTTP POST request to act like that pipe, sending data from one service to the next immediately upon the occurrence of an event connecting services in a fundamentally event-driven, instantaneous way.
And the old way that this new pattern was specifically designed to replace was inefficient polling. Anyone who has ever built a monitoring dashboard or a background job status checker that relies on a tight polling loop knows that's soul-crushing inefficiency.
Oh, absolutely.
Polling requires the client, in this case the destination service, to repeatedly check the source server. Has the order shipped yet? Has the file converted yet? Do you have new data? Do you have new data?
It's inherently wasteful for several reasons. First, you dramatically increase network load because you're generating unnecessary requests. You're basically sending 99 no messages for everyone. Yes.
And paying for all of them.
And paying for all of them. Second, it introduces latency because the destination only finds out about the event at the next scheduled check interval, which might be seconds or even minutes after the event actually happens.
So you're paying for wasted compute and bandwidth just to wait.
Precisely.
Webhooks eliminated that overhead entirely. The source service proactively pushes the complete message instantly upon the event occurring, cutting out the cyclical waste and achieving near-instantaneous notification. This shift is what made real-time integration scalable.
For sure. Now, when we look at any service that uses webhooks, we can classify the message flow based on the direction relative to that service. We talk about incoming versus outgoing webhooks.
Okay, let's break that down.
Let's consider service B as our frame of reference. If service A is sending a message to service B, so the message arrives at our reference service, that is an incoming webhook for service B.
Makes sense. So conversely, if service B is integrated with, say, a service C, and service B is the one sending the message to trigger an action elsewhere, the message leaves the reference service.
Then that would be an outgoing webhook for service B.
The key is understanding the service you are looking at. If it's receiving, it's incoming. If it's sending, it's outgoing.
Exactly. And this classification helps map out incredibly complex architectures where one single service might be a destination for 50 different partners and a source for 50 others.
Wow.
And regardless of the direction, the destination service needs to subscribe to the event stream. This subscription process can be done in one of 2 main ways.
The first is manual, or as we call it, out-of-band configuration. This means an administrator or developer physically goes into the source system's configuration panel or database and manually enters the callback URL.
It's out of band because it happens outside of the typical automated API data channel.
Right. This method is often used for internal systems or when you have a small, trusted group of consumers.
And the second and far more scalable method is automatic registration.
The self-service model.
The self-service model. The destination service sends a single explicit HTTP POST request to a designated registration endpoint on the source service. This request contains the destination's callback URL and usually specifies the exact types of events it wants to subscribe to.
So it could say, I only want order.created and user.deleted, but nothing else.
Exactly. And that's what powers scalable public APIs. That automatic registration is the essence of agility. The destination says, here's my phone number. Please only call me when you have news about X, Y, or Z.
Okay, let's solidify this abstract flow with a real-world, highly detailed case study. We're going to use the classic bidirectional integration example, the fictitious books.example.com, which is an online bookstore, and its strategic partner, the automated distribution center warehouse.example.com.
Right. And to make the system work, both services have to be engineered to handle both source and destination roles at different times.
So they both need their own callbacks.
Correct. Both services must define their own public-facing callback URLs. For the bookstore, they need to know when their orders are moving. So the bookstore defines its callback URL, maybe order status.
Okay, that makes sense.
And this endpoint is designed to receive status updates like dispatched, in transit, delivered.
And the warehouse needs to know when a new order drops. So the warehouse defines its callback URL, let's call it orders accept. This endpoint is designed to receive the initial notification that a customer placed an order.
Perfect. So now for the two-way registration flow. First, the bookstore needs updates from the warehouse. The bookstore registers its order status URL with the warehouse's registration endpoint, essentially saying, when you process order 123, send status changes here.
And then, simultaneously, the warehouse wants to know about new orders from the bookstore. So the warehouse registers its order accept URL with the bookstore's registration endpoint, saying, send all new order webhooks to this URL immediately.
And with registration complete, let's trace the event flow, which truly demonstrates the power of the push model.
Let's do it.
Step 1. A customer clicks buy on the bookstore site. The event, order.created, occurs in the books.example.com database.
Step 2. This order.created event is configured to trigger an outgoing webhook from the bookstore. The bookstore instantly generates an HTTP POC request containing the order details in the payload and sends it to warehouse.example.com's registered orders accept endpoint.
And the warehouse receives the message and immediately returns a 200 OK acknowledgement.
Right. Got to have the acknowledgement.
Step 3. The warehouse processes the order. As it fulfills the order, its own internal state changes generate a chain of events. Order.dispatched. It left the loading dock, followed by order. In transit, it's on the truck. And finally, order.delivered.
Okay.
The tracking confirms completion.
Step 4. Since the bookstore subscribed to these events, the warehouse now acts as the source, triggering an outgoing webhook for each event. These are separate POST requests sent back to the bookstore's order status callback URL.
And the bookstore receives them, updates the customer-facing status, and acknowledges each one with a 200 OK response.
The loop is complete. We replaced potentially dozens of polling checks with just 4 instant pushes.
Yeah. And this specific universal integration procedure boils down to 4 key requirements for implementation that you, as the engineer, need to be mindful of.
All right, what are they?
First, the destination service setup. It must implement that robust public-facing HTTP endpoint, the callback URL, and critically, it must contain a shared secret key.
A cryptographic key.
A symmetric cryptographic key that is identical to the one known by the source service. This secret never leaves the two services. It's the key to trust.
Okay, that's number 1. What's 2?
Number 2 is the source service setup. It must integrate the destination's callback URL, and it must hold that identical shared secret. This secret is used by the source service to actively sign their request's payload before it's sent.
So it's proving its identity.
Exactly. Third is the execution. The source service has to handle the logic of triggering the webhook immediately when the event occurs and generating the entire HTTP request with the necessary headers.
And 4.
And finally, fourth, verification and acknowledgement. The destination service performs the crucial security check using the shared secret to verify the received message. Only after verification does it process the data, and only then does it return the success acknowledgement, the HTTP 200.
And if any of that fails, security, processing, delivery, it sends back an error code.
It has to, yeah. That tells the source something went wrong.
That acknowledgement loop brings us perfectly to the next logical step, security. We have granted an external service, the warehouse, the ability to send requests directly into our internal infrastructure, our order status endpoint. This is powerful, but it's also, it's a massive security risk. How do we ensure the payload hasn't been tampered with and that the message is truly from the warehouse and not some malicious actor who simply found our callback URL?
Right. Security for webhooks must operate on 2 layers. The first and most fundamental is TLS transport layer security.
HTTPS.
Always use HTTPS. This ensures encryption, integrity, and basic authenticity for the data while it is in transit over the network.
But that only protects the tunnel.
Exactly. Once the data reaches your server, you need to verify the integrity and authenticity of the payload itself at the application layer. For that, we rely heavily on HMAs, the hash-based message authentication code.
This is a crucial distinction. Why is HMAC the standard here, rather than a simpler API key or a bearer token, which we see in traditional request response OPIs?
It's a matter of performance in the threat model. In a standard API, when a client sends an API key, the server has time to look up that key in a database, check permissions, validate the user, all that stuff.
Right, it's a synchronous lookup.
It is. But with webhooks, we have asynchronous high-volume pushes. We need an extremely fast, stateless method for the destination to confirm two things. One, the sender possesses the shared secret, and two, the message payload hasn't been altered.
And HMA does both.
HMAC provides this. It uses a cryptographic hash function like SHA-256 and the shared secret, that webhook secret we defined, to create a unique signature of the message payload. A source service calculates the signature, sends it in a header.
And then the destination service recalculates it on arrival.
Exactly. If the two signatures match, authenticity and integrity are confirmed instantly without any database query. This confirms the message is exactly what the source sent.
This need for robust, standardized security measures led to the creation of the standard webhook specification. This project is attempting to normalize the implementation so that developers don't have to reinvent the wheel every time they integrate a new partner.
It is, and following this standard means requiring specific HTTP headers for every webhook request. The standard mandates that the destination service check for 3 specific headers to perform its verification: webhook ID, webhook signature, and webhook timestamp.
Okay, let's walk through the actual 4-step verification process required by the standard. This is the logic that executes on the destination side, and understanding the order and purpose of these checks is paramount to building a secure endpoint.
All right. Step 1, payload size check.
Before anything else.
Before doing any heavy cryptographic work, the destination should perform a quick sanity check. Industry recommendations typically set a payload size limit around, say, 20 kilobytes.
And if it's bigger.
If the payload is too large, the destination should immediately reject it with an HTTP status code 413, content too large. This isn't a security measure against forging signatures, but it's a vital protection against denial of service attacks intended to consume your processing resources.
Smart. Okay, what's step 2?
Step 2, header presence and format check. We need to ensure that the request actually follows the standard. The destination must confirm the presence of all 3 required headers: webhook ID, webhook signature, and webhook timestamp.
And if one's missing?
If any are missing or malformed, the destination must return a status code 400, bad request. I mean, if the necessary information isn't present, we can't proceed to verify the message.
Okay.
Step 3.
Step 3, and this is where we prevent the most insidious attack, is the timestamp check for replay attack prevention. The destination service parses the timestamp from the webhook timestamp header. It then calculates the age of the request.
This is critical. Why do we care about the age of the request?
Because an attacker could capture a perfectly valid webhook message, including the signed payload, the ID, and the signature, and try to resend it or replay it later. If that message was an order.created event, a successful replay could trigger duplicate charges or duplicate fulfillment.
Which would be disastrous. Completely. By enforcing a narrow time window, say 5 seconds, which is a common implementation threshold, we prevent this. If the request timestamp is older than 5 seconds, the request is expired and we return a status code 400.
So that 5-second window is a trade-off.
It's a careful trade-off, yeah. It's short enough to prevent a network capture and resent attack, but it's long enough to account for standard network jitter and clock drift between 2 physically separate servers.
That makes perfect sense. The timestamp is the first line of defense against time-based fraud. Okay, so now we're on to the final step.
Now for step 4, signature creation and comparison. This is the core HMAC security measure. The destination service takes the raw request body, the payload, the webhook ID, and the webhook timestamp, concatenates them into a single string, and then calculates the expected HMAC hash using the shared secret key.
And then it compares that to what it received.
It then compares this newly calculated hash against the hash provided in the received webhook signature header. If they don't match, it means one of 2 things. Either the message was tampered with in transit.
Data integrity is gone.
Or the sender does not possess the shared secret.
Authenticity is gone.
Right. And in either case, the destination must reject the request with HTTP status code 401 unauthorized.
This whole process demonstrates just how robust the security model must be. But what about the risks inherent to managing this architecture? We focused on the security of the communication, but we have to discuss the management of the secrets themselves.
Oh, absolutely. The primary risk revolves around the shared secret. If that webhook secret is leaked or stored insecurely in a public repository or exposed through poor logging practices, the entire security model it collapses.
Right. An attacker who gets that secret can forge valid webhooks and bypass all our checks instantly.
Instantly. Strong secrets management using infrastructure secrets managers or encrypted vaults is mandatory here. It's not optional.
And what about error handling?
Right.
When implementing the destination endpoint, developers need to be mindful of error reporting. For external partners consuming your webhooks, you should never expose specific details like HMAC mismatch or shared secret not found.
Because that helps the attackers.
It helps them probe your system. A generic 401 unauthorized is always the safe choice for public-facing endpoints.
You mentioned one final, often controversial security measure used when dealing with specific known partners. That's the use of an IP address allow list.
It is a controversial but common measure, yeah. By using an IP address allow list, you configure your firewall to limit messages only to trusted source IP addresses provided by your partner. It's an effective added layer of defense against completely unsolicited traffic.
But wait, isn't relying on an IP allow list a brittle security strategy today? What happens if the source service, like a major cloud-native partner, scales up and changes its outbound IP range frequently?
Doesn't that force us, the destination, to constantly update our firewall rules, leading to operational complexity and potential downtime every time their infrastructure shifts?
Absolutely. That's the trade-off. It only works well if the source infrastructure is stable and publishes its IP ranges reliably, like certain managed services do.
But if they're auto-scaling?
If your partner is running services that auto-scale or use serverless architectures where the outbound IP addresses are dynamic or belong to massive cloud provider ranges, an allow list becomes quickly unusable. It's a great defense for known, stable environments, but it fails spectacularly in highly elastic ones.
That's crucial context. Okay, we've secured the perimeter. Now let's turn to the developer experience. Even with excellent security, if integration is difficult, the system won't be adopted. This is where standardized documentation comes in. So what does this highly detailed communication standard mean for the developers trying to connect to a webhook API?
Well, the Open API Specification, or OAS, the standard used to describe RESTful APIs, has evolved specifically to handle webhooks, starting robustly with version 3.0. It uses dedicated fields, webhooks, and callbacks.
And why is that so powerful?
It's powerful because it allows the OAS document to describe the architecture of the push mechanism. Normally, OAS describes an endpoint that the client calls. Here, the webhooks field describes the request that the source service will initiate and send to the destination.
So it's describing the other side of the conversation.
Exactly. It meticulously defines the PS method, the required parameters, and the complete request body schema, the JSON payload containing the event data. So the developer reading the documentation sees exactly what will be sent to their system, down to the header level, rather than having to guess or rely on verbose text descriptions.
And does it describe the response too?
Precisely. The OAS document also defines the expected responses, the acknowledgement that the destination service must return. It spells out that a 200 OK means success, and more importantly, it codifies the necessary security failure responses. 400 bad request, 401 unauthorized, and 413 content too large.
So both parties understand the contract of failure recovery.
Right. And what's helpful for developers is that OAS uses reference fields, the ref notation, extensively. This allows for reuse of component definitions.
How so?
For example, those critical security headers we just discussed, webhook id, webhook signature, and webhook timestamp, can be defined just once in the component section and then referenced across every single webhook event, ensuring consistency.
That's great.
And this isn't just theory. Tools like Swagger Editor allow developers to write and validate their OAS documents in real time, providing a live, human-readable preview of the specification. This significantly lowers the barrier to entry for integration engineers.
A quick safety note on those online tools, though. While they're helpful, you should never handle or define sensitive data, especially shared secrets, which should be in vault systems, in an external online validation environment.
Yes.
Use local tools if your definitions contain sensitive configuration data.
A vital warning indeed.
Let's shift to the operational side and summarize the core trade-offs. Webhooks are undeniably convenient. They solve the polling problem, but they introduce significant architectural complexity that often goes unacknowledged until the system fails. We'll start with the advantages. What stands out to you as the biggest win?
For me, the first major advantage is the mandatory message acknowledgement. The destination service must respond to every message. This strengthens overall system resilience.
How so?
If the response is anything other than a successful 200 series code, the source knows that message failed delivery or processing and can flag it for immediate retrying. This is inherently more robust than, say, a fire and forget message broker API.
Okay, that's a big one. What else?
Second, the obvious win. Elimination of polling. We've discussed this at length, but the instant event-based delivery avoids network waste, reduces latency, and saves significant compute costs for both the source and the destination.
Third, they are inherently event-driven. The communication is instantaneous, triggered by a specific state change. This is perfect for process automation. If a critical service update happens, the notification is immediate, not delayed by a polling interval.
And finally, they enable asynchronous processing and fan-out architecture elegantly. Webhooks allow one service, the source, to instantly notify multiple downstream partners one-to-many without the source having to wait for any of them to finish their processing.
The source sends the push, gets its 200 OK, and just moves on.
Exactly. It moves on.
Now let's flip the coin and look at the complexity behind the convenience, the disadvantages that often require significant engineering investment. The first major hurdle is versioning challenges.
Oh, this is a huge one.
Webhooks introduce incredibly tight coupling. The destination service is hard-coded to expect a specific callback URL and a highly specific JSON payload structure. If the source changes anything, a field name, a data type, the URL itself, the integration instantly breaks for potentially dozens of consumers.
It's a maintenance nightmare.
It is. And version management is a constant operational headache. We have two primary solutions for payload versioning, and neither of them is perfect.
That's true. Solution one is dual payload sending. For a period of time, the source service sends two distinct versions of the payload for the same event. So, for example, the source might send the old format, v1, with first name and last name, and also the new format, v2, with a single full name field.
The advantage there is safety. The destination can migrate at its leisure, but the engineering overhead is significant. You're asking the destination to receive two separate messages for one logical event, and the source has to maintain and serialize two distinct data models for every single supported event.
Right. That maintenance burden on the source can quickly become an unmanageable tax on development speed.
Okay, so what's solution two?
Solution two is optional fields and deprecation. Instead of sending two messages, you simply add new fields to the existing payload, making them optional to consume. So you add full name to the payload that still contains the deprecated first name and last name.
And you tell the destination to start using the new field and ignore the old ones.
Right. This is cleaner, but it still requires a clear, pre-communicated switchover date. The source service informs consumers. By October 1st, we will stop sending first name. The destination must migrate by that date or risk breaking.
So most successful platforms use a combination of these methods, I'd imagine.
They do. Optional fields for minor changes and entirely new URLs or endpoints like v2 order status for major breaking changes.
The second major disadvantage is arguably the most complex architectural trade-off of all, the lack of built-in message delivery guarantees.
This is so critical. While the destination acknowledges the message, if the message is not acknowledged because the destination server is temporarily unreachable, down for maintenance, or there's a network failure, the source service cannot simply forget about it.
It has to guarantee delivery.
It has to, which means the burden of resilience falls squarely on the source.
And this means the source service suddenly requires significant internal infrastructure. It needs dedicated components for message storage to hold the failed message, a sophisticated queuing and scheduling system to manage retry attempts, and robust exponential back-off logic to avoid overwhelming the destination service once it comes back online.
And the complexity doesn't stop there. Because the source is retrying failed messages, the destination service must be idempotent.
Which means...
Idempotency means that processing the same message multiple times must have the exact same result as processing it just once.
Okay, so if the source retries the order.created webhook, maybe because the initial 200 OK acknowledgement got lost in a network hiccup, The destination must have logic to check if that specific webhook has already been processed and successfully acknowledged in its internal database.
Right. And if it has, the destination must simply return a 200 OK without reprocessing the order, thereby preventing a duplicate charge or fulfillment.
That's a massive engineering overhead.
It is. In alternative architectures, like those using managed message brokers, that queuing, scheduling, and sometimes even the duplicate checking is handled by the broker itself. With webhooks, you have to build all that resilience infrastructure in-house.
So it's convenient for the consumer, but a real challenge for the provider.
A huge challenge.
And the final disadvantage is the lack of universal standards. We talked about the standard webhooks project, but ultimately adoption isn't total, is it?
That's right. Despite the excellent effort to standardize, webhooks remain an evolving architectural pattern. This means implementation variability is high. If you integrate with 5 different partners, you might find 5 slightly different ways they calculate the signature, 5 different headers, and 5 different retry schedules.
Which increases the integration cost for every new partner you onboard.
It does.
So we've successfully navigated the entire landscape, from the inspiration of Unix pipes and the core push model to the granular mandatory security checks required by HMEC and the painful trade-offs of building idempotency. Let's wrap up by highlighting the primary use cases where the complexity is worth the investment.
Sounds good. First and foremost is the large-scale service-to-service integration we demonstrated, like e-commerce and logistics. Whenever you need instantaneous data synchronization across organizational boundaries, webhooks are essential.
What's next?
Second is process automation. Anytime a single event needs to kick off a complex, multi-step pipeline, triggering a deployment pipeline on a new code commit, or automatically creating a user account in 5 different internal systems upon registration, webhooks are the lightweight, instantaneous trigger.
Third, they are the foundation of modern general notifications and logging. If a monitoring service needs to alert an engineer instantly about a system failure, or if a service needs to log event data to a centralized analytics platform without delay, webhooks provide the rapid fire-and-forget mechanism needed.
And finally, webhooks are ideal for long-running asynchronous processes.
Like video encoding.
Exactly. If you start a process that takes a substantial amount of time, like rendering a high-resolution video file or generating a complex financial report, the client can initiate the job and immediately disconnect. The source service then uses a webhook to deliver the final success or failure notification, or even progress updates, eliminating the need for the client to poll for hours.
That brings us to our final thought for you, the listener, to explore further. We established that webhooks solve the latency and cost problems of polling by guaranteeing instant event-driven communication. But they achieve this by shifting the burden of building highly resilient infrastructure message storage, queuing, handling duplicates onto the source service. So, given that immense internal engineering complexity required to guarantee delivery and handle potential idempotency issues, when is the extra work required by building your own webhook infrastructure worth the trade-off compared to simply using a managed broker system, like a service bus or a dedicated queue that handles all that queuing, guarantee, and resilience infrastructure for you?
That's the question.
And how high must the cost of inefficient polling be to justify building all that complex internal logic yourself? That's the core architectural question at scale, something for you to mull or explore on your own. Thank you for joining us for this deep dive into webhooks. We hope you feel significantly more well-informed and ready to tackle your next system integration challenge with robust security and clear documentation. We'll see you next time.